Okay, so we can start the recording if you haven't already. But welcome everyone. This is our third or fourth meeting in January. I believe third. I'm not sure. And we'll be continuing our unit on artificial intelligence. Today we'll be mainly covering regression. It's a common topic needed for most AI programs or ML programs to run. You can also learn it in other math classes like calculus, statistics. Might go over this topic a little bit. So, what is our problem for today? So, our problem is, if you look at the screen, what should I watch this Friday, right? And it has a movie, and you have a rating, and you're not sure whether you want to watch this movie or not. Or you could watch this movie and its own rating, right? And so the goal is to predict the movie rating automatically. So you want to look at a movie and predict its rating. How do we do that? Or another problem could be how many followers will I get? So you're given in some input. You can see it has 282 votes on this post, 5 comments, 67 favorites, and you're trying to predict or output how many followers you can get back. Another problem or goal is the price of this house. So you'll be given some input value, for example, the location, where it is, other data about the house, and you want to predict the price of it. So what do all of these problems have in common? The movie, the post, or the price of the house? They all have continuous outputs, and we can call these T. So for example, a rating would be a number between 0 to 10. A number of followers, continuous, and the house price is continuous. So last meeting we covered the difference between continuous and discrete. Right. So continuous is a number that it can fluctuate in between, and discrete has a set value. Right. So what do you need to predict these outputs? Predicting outputs is called regression. Features or inputs, we'll call these X, and training examples, many XI, or for which TI is known. For example, many movies to watch, for which you know the rating. That could be your input. A model, which would mean a function, so relationship between X and T, right? So input X and output T, so you need a function. A loss or a cost or an objective function, which tells us how well models, sorry, which tells us how well our models approximates the training samples, right? So we need like accuracy kind of optimization, a way of finding the parameters of our model. So today we'll be looking at linear regression. It's a form of regression. Obviously, linear. If you're familiar with any sort of algebra, there's a linear function would be a function in which the x and y plot points are in a straight line. It's the same concept here. So linear regression with continuous outputs, and it's a simple linear model. So we're going to use this linear regression topic to introduce some key concepts, including loss functions, generalization, optimization, model complexity, and regularization. So circles on this graph here, we have t and x. Circles would be the data points or the training samples that are given to us. The data points are uniform in x, but may be displaced in y. So we can use a function to displace this ML model. T of x equals f of x plus e, and that e stands for some noise, so the a little bit of inaccuracies inside each model or inside each program. And our goal is we want to find a curve that can fit all of these points or fit best fit. So back in algebra, you do use something called line of best fit, where you plot certain data points and you want to find a line of best fit. And the whole idea behind that is once you have a line of best fit, you can predict at this x value, if I put this x value input, I'll receive this y value input. So it's the same thing here, except here it's not linear. It's more of a quadratic, if you will. So how will we parameterize this model? What loss slash or objective function should we use to judge the fit? And how do we optimize fit to unseen test data, so generalization? Okay, so an example of this would be Boston housing data. So this is back to that price of the house example we looked at. Estimate median house price in a neighborhood based on neighborhood statistics. So first you want to look at the first possible attribute feature. So per capita crime rate, right? So the crime rate obviously plays a crucial role in the price of a house, right? So here we have a graph with the per capita crime rate on the x-axis and the median house price on the y-axis. And you can use this to predict other house prices in the other neighborhoods. Is this a good input to predict house prices? And I would argue, yes, it is, because, like I stated, the crime rate has a direct correlation with the price of a house. So represent the data. Data is described as pairs D, and we have sets. So x1, t1, x2, t2, all the way to xn, tn. And like we reviewed in last meeting, these are not exponents. They're actually just kind of like superscripts, just to denote first, second value of x and for t respectively. So x as an element of R, that's what that symbol means, is an input feature, per capita crime rate. And T as an element of R is the target output, so median house price. And I simply indicates the training samples. We have N in this case. We have N training samples in this case. So here T is continuous, so we can classify it as a regression problem. And the model outputs Y, which is an estimate of T. So here we have a function down below. Y of x equals W0 plus W1x. So what type of model did we use? Again, this can be, you can look at it kind of like y equals mx plus b type of situation here, except this is a function y of x. So W0 is the initial starting point, W1 is the slope, x is the x variable, and y of x output is the output function. So what type of model do we choose? So divide the dataset into training and testing samples. Use the training examples to construct hypotheses or function approximator that maps x to predicted y. Evaluate hypothesis on test sets. So now we're going to cover the concept of noise. A simple model typically does not exactly fit the data. Lack of fit can be considered noise. Sources of noise can include impression in data attributes, input noise, example noise in per capita crime, errors in data targets, for example mislabeling or noise in house prices, additional attributes not taken into account by data attributes affect target values, latent variables. In this example, what else could affect house prices? Model may be too simple to account for data targets. So now we're going to be looking at least squares regression. So here we define a model. Y of x is equal to a function x comma w. We define a model, and we have the linear regression line right here. So whenever we're using linear regression, the formula is similar to the slope-intercept form that we learned back in algebra. Y of x equals w0 plus w1x. And here we have our linear regression line. So we have a line of best fit that plots all these points, and this is kind of the average, right? Standard loss cost objective function measures the squared error between y and the true value t. So back to this. This only works when we have when our plots follow a linear regression model. And if they're not following a linear regression model, what we normally use is least squares regression. So the way this works is we take this formula here. L of w equals summation from n equals 1 to big N, tn minus y xn whole squared. So for a particular hypothesis, y of x defined by a choice of w drawn in red, what does this loss represent geometrically? So these would be the square lengths of the green vertical lines, right? As you can see here on this graph to my right, we have x on the x-axis, t on the y-axis, and we have three certain points, right? The points being represented in the blue circles, and we have our line of best fit, which we use least square regression to find out. And why is this line of best fit? Because we are taking the value from the dot to the value in the red line, the y values, and then squaring that. That hence gives the name least squared regression. So how do we obtain weights W for W0 and W1? Oh, okay. So someone joined a bit late. That's fine. We use what's called gradient descent, which we'll discuss next week. So, so how do we, here, so, oh, okay, he just joined left. So I'm going to re-explain. Fine. Optimizing the objective. One straightforward method would be gradient descent. Initialize the W randomly. Repeatedly update the W based on the gradient with this formula. And here we'd have to use a bit of calculus, which that's what this derivative is, but that we'll go into that later. Lambda is learning rate, for which a single training case. This gives the LMS update rule. So right here, this is that update rule being implied. This it does imply and use a bit of calculus for this gradient descent model, but it won't be too much. And next week when we go over it, we'll try to explain it. So even if you do not take or know any calculus, you can still understand. Now, as this error approaches zero, so does the update. W stops changing. So optimizing across the data set, training set. There's two ways to generalize for there's two ways to generalize this for all examples in training set. Batch updates, sum or average updates across every example, and then change the parameter values. Being shown right here. Got a bit messed up with the formatting, but that's alright. Or stochastic, I can't pronounce that, sorry, or online updates. So update the parameters for each training case in turn according to its own gradients. So algorithm one is stochastic gradient descent. Randomly shuffle examples into the training set for I equals 1 to n, do update W equals W plus 2 lambda T minus X, I being just the a specific value, and you update for a linear model. And then here you end the for loop. Now there's two ways to generalize this for all examples in the training set. Batch updates, which would be a sum or average updates across every example n, then change the parameter value, or the stochastic online updates, update the parameters for each training case in turn according to its own gradients. So under the second update method, we have an underlying assumption that sample is independent and identically distributed, IID. So what would be an analytical solution for this? Some objectives, we can also find the optimal solution analytically. This is the case for least squared regression, linear least squared regression. Now, how do we do this? We compute the derivatives of the point, and derivatives would be a calculus concept. It's basically the rate of change. So you can think of it kind of like a slope. They compute the derivatives of the objective WRT, W, and equate with 0. Now you define T with the set, X with the set, sorry, image just got distorted a bit. And then use this formula, W equals XT, X to the negative first, XT, T, and work it out. Now, for multidimensional inputs, one method of extending the model is to consider other input dimensions. So in this formula, y of x equals W0 plus W1x1 plus W2x2. So essentially, you're increasing the input size. So back to this Boston housing example, we can look at the number of rooms. So previously, we used the crime rate to output a price value. Here we're using the number of rooms in a house to output the price value. And here we see our graph plotted with x and y points. So linear regression with multidimensional inputs. Imagine now we want to predict the median house price from these multidimensional observations. Each house point is data n with observations indexed by j. So in the form below you can see xn equals 1 and x plus, and then it keeps going basically in the list for n number of data points. We can incorporate bias W0 into W by using x0 equals 1. And so by converting the first formula to the second formula, you're just accounting for any bias in the model. Now, how can we solve? We can solve for W, right? So how do we do this? We can use gradient descent to solve for each coefficient or compute W. And analytically, how does this solution change? So what are some more powerful models? What if our linear model is not good? How can we create a more complicated model? For example, if the function does not follow a linear form, function is leaning towards more of a quadratic form, how do we do that? We can create, so fitting a polynomial, we can create a more complicated model by defining input variables that are combinations of components of x. Example, so an m to the order of polynomial function of one-dimensional feature x. So here's our equation below. Y and takes in two input parameters xw equals w0 plus summation from j equals 1 all the way to m w j xj, where xj is the jth power of x. We can use the same approach to optimize for weights w. And how do we do that? As seen below. So if you just take a look at the images below, we can see which line best fits. So for example, the blue circles here are the data points. So in the top left, you have the same data points and you have that green line, and the red line is the line of best fit. But this line of best fit does not do a good job of accurately representing our data model, as it is linear with a slope of 0, but it does not it does not like go not even close to any of the data points, right? Moving on to the top right, this is linear with a negative slope, and this kind of works, but still, our points are not that close to the line, and our least square regression, if we use that least square regression formula, for example, take this point right here, find the y value from this point to the red line of best fit, and then square that. That would be obnoxiously high because just the line of best fit is not the best. It's not the line of best fit here. Moving on to the best choice, which would be the choice in the bottom left. So here we have a somewhat quadratic or polynomial function with the blue data points, and with this red line, it comes pretty close to each of the blue points. And again, the way to check this is like the least square regression line formula. So you check all the data points and find its y distance from the point to the red line, square that, and then the sum of all the squares, that was the summation, whichever one that is lowest. And this red one is just completely distorted. It hits all the points, yes, but it's not a line of best fit. Now, generalization. What is generalization? Generalization is the model's ability to predict the held out data, what is happening. In this graph, we have the training in the blue and the test in the red. Now, our model with m equals 9 overfits the data. So models also noise. And this is not a problem if we have lots and lots of data samples or training samples, but and we are displaying that right here, so if n equals 15, this is fine, even when n equals 9 and it's overfitting the data. Oh, sorry, this is not fine, right? But then with n equals 100, that's a lot more data samples. So even if it's overfitting the data with a strength of 9, you are still getting a line of best fit, which is fairly accurate. Now let's look at estimated weights for various m in the case of fewer examples. The weights are becoming huge to compensate for the noise, and one way of dealing with this is to encourage the weights to be small. This way, no input dimension will have too much influence on the prediction. This specific method is called regularization. Regularizing least squares. So increasing the input features is one way increasing the input features this way can complicate the model considerably. And our goal is to select the appropriate model complexity automatically. So we use our standard approach, regularization, and I can explain this formula to you guys. So L of function W equals T, and we have another summation here, n to n equals 1 to n of T to n, where minus W0, so the initial W value, and plus 2W1, so the second W value, plus xt, plus that last part, alpha W. Sorry about this. This formula gets a bit distorted with the superscripts and summations and whatnot. So intuition. Since we are minimizing the loss, the second term will encourage smaller values in W. And the penalty on the squared weights is known as ridge regression in statistics. And this leads to a modified update rule for gradient descent with the formula right here. It's pretty much the same formula, just as the normal gradient descent one. So but I can go over it one more time. So W equals W plus 2 lambda. Again, the summation got distorted. But n equals summation from n equals 1 to big N, the nth term of t minus the nth term of y, x minus times x minus alpha W. Also has an analytical solution right here, and you can verify it. So regularized least squares is better generalization, but you have to choose alpha carefully, which is the strength. So now we'll move on to 1D, 1D regression illustrates key concepts. Data fits. So is the linear model the best model selection? Simple models may not capture all the important variations signal in the data. So that would mean we have an underfit between the line of best fit and the data points. And more complex models may overfit the training data, so fit only the signal, but also the noise in the data, especially if we don't have enough training samples to constrain the model. One method of assessing fit test generalization would be the model's ability to predict the held out data. Optimization in this model is very essential as stochastic and batch iterative approaches analytic when available. So that brings us to what movie will you watch? And that was pretty much the end of it. This meeting was a bit short because I kind of ran through linear regression and covered a bit of gradient descent. But there's only one person here, so the other people that missed the meeting hopefully did not miss too much, and we'll send out the slides as well. But yeah, that pretty much covers today's meeting. It'll be we can review some of these topics later on, and we'll move on to gradient descent next meeting. But thank you, and yeah, you're free to leave now. Oh, sorry. Which side would that be? Okay, I see that. Can you go? Oh, you're taking notes?
95.
95, sorry. Yeah,
Thank you.
yeah, sorry. And we will,
95.
yeah, we will post the slides on the club update, so you can go over that as well. As well
Okay.
as if you have any in-depth questions about any of these topics here, yeah. I'd also recommend messaging Arnav, the other president in the club. He's the most familiar with artificial intelligence. He'll probably be able to guide you through it.
Okay.
Yeah.
Okay. Thank you. I got it.
Okay. Yeah. So post this in YouTube video and just the slides. If you have any further questions, you can ask Arnav.
Okay.
Yeah. All right then. See you next week.
Thank you.